Live now? I think we had a minor technical glitch there, folks.
There we go. Okay.
Okay, sorry about that, folks. We were having minor technical difficulties. I tried something new and it failed. Actually, I now know how to make it work, so it didn't fail completely. Y'all missed our whole opening spiel. Do we want to do it again?
Sure. So welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and here with me
is Robert Moore.
Okay, Robert, where are we? You want to tell folks?
Okay, I'll tell folks this time. We're on the campus of the University of North Dakota. We're in Grand Forks, North Dakota. And apparently we're getting lots of echoes, so I will do a little tuning. That might have been too much. How's that? But anyway, getting back, we're in Grand Forks, North Dakota, which is northeastern North Dakota. And that's on the United States, as Wayne was saying earlier, the continent of North America, the Earth, the solar system.
Keep going.
The Andromeda Galaxy, the Milky Way Galaxy. And
the local
group and the universe.
There you go. Now there could be other universes, so we should call it the local universe, which means our universe.
Right. So,
now, did you notice how nice the weather is today?
I did. I mean, past 2 days, things have actually been melting here. That's really not supposed to happen in February, is it?
Well, I love it.
Oh, well, I'm not really complaining. I'm just kind of surprised.
Well, it's really nice weather, and anybody who's interested in coming to, so it looks like we still have echoes.
Yeah, we still have echoes. So let me try doing this.
Try to do a little bit of a technical justification here.
Yeah, doing some technical adjusting. How's that one doing? It may be that we got 2 microphones going. And something we'll have to work out.
Okay, so let's kind of continue on.
Yeah.
So speaking about the temperature, Robert, do you know the difference between temperature and heat?
I do, actually.
Okay, you want to define those?
Yeah, I'm doing a very loose definition here, but temperature is generally kind of a still echoes. Heat is a measure of the one type of internal energy. In other words, it's the energy of particles that are make up the substance that you're trying to take the temperature of. Oh, wait, there's that temperature thing. So the temperature is a proxy, a numerical value associated with that heat. But, because heat is usually much more difficult to measure than a temperature.
Right. Well, you can use a sort of, still echoing. I don't know why you have the echo.
I don't know why we have the echo. Was it present in the last episodes?
No, not that I noticed.
So something is different, but there's no telling what.
You want to turn down your microphone a little
Yeah, I've been turning it down.
Oh, okay. Turn it down until it's off. Then.
Well, that's pretty much where it is now. It's off.
Okay. And this is not plugged in, right?
That's not plugged in.
Okay.
So it may just be the room, and we're finally getting things.
Well, the room hasn't changed, but.
Right, but I can hear the echoes actually in the room, and it's.
Yeah, I'm not sure where it's coming from, but.
We need sound reduction in the room.
There we go. But, okay, so.
We'll try to keep going on. I'm sorry about the poor quality.
Now, the temperature itself, and the way you can think about it in terms of heat, imagine that you had a cup of water.
No, we do not have speakers on.
No.
So there is no feedback at all. There's no source of it. No speakers on in this room. Just the 2 mics, and we've been having the 2 mics. So I'm not echoing.
Robert's not echoing. Am I echoing, Dean? Do you notice if I'm echoing? I assume that message meant, Robert, you were the one that was echoing.
Yeah.
Okay, so let's move on a little bit till we see
Then we'll see how that goes.
Okay, so you are echoing yes.
Okay. So,
Yes, so I'm echoing.
So turn yours down a little bit.
Okay, I'll try that.
We'll try that.
Echoing each other.
Okay. And that's the problem with two mics, but if we don't do it, then one of us isn't
I'll
able
turn
to be
this
heard.
How about now? Any better? Silence.
Silence.
No echoing, you know, when you have silence.
Right. Well, there's also a little bit of a lag between
Yeah.
when we're saying things and when it actually goes out.
Okay. Maybe we'll try a headset next time. We don't have any.
Yeah, we may have to do that.
Yeah.
That's
That's better. Dean says it's better, so let's continue on.
Okay.
Okay, so getting back to the discussion of heat versus temperature. So imagine that you had a cup full of water. Okay. And let's say it has a temperature of about 70 Fahrenheit.
Okay.
And let's say you filled up your bathtub, and that is also at a temperature of 70 Fahrenheit. So clearly they have the same temperature.
Right.
Which one has the most heat?
Let's see. It was a cup of water in a bathtub, right?
Yeah,
Yeah, I'm going to go with the bathtub.
go with the bathtub. So the way to think about it is that temperature is a measurement of the average motion of particles that make up whatever substance you're measuring the temperature of. So for example, you can think of water and water molecules. So those water molecules are moving around, and the average energy of motion, in physics we call that kinetic energy. That's what we really mean by temperature. So in a cup of water at 70 degrees Fahrenheit, let's say, those water molecules are moving around with a certain average speed. And if you have a bathtub full of water, and the temperature of that water is also at 70 degrees, then those molecules also have the same average kinetic energy.
Right.
But the heat is different. There's a lot more heat in that tub full of water than there would be in that cup of water. And the reason is you add up the contribution of all of the particles or molecules in this case that make up your substance. And there's clearly a lot more water molecules in your tub of water than it would be in just a cup full of water.
Absolutely.
So the overall heat, when you add all the contributions up for the individual particles, is way larger for that tub full of water than it is for the cup. Okay, so that's the difference between temperature and heat. And I'm going to ask you another question, Robert, see if you know this.
I'll blow this one too.
Okay. Did you know that black holes have a temperature?
I did not until we started discussing this recently because someone asked you that question.
Right. So the way to think about it is a black hole, from the very nature of black holes, and Robert, if you want to pull up the first slide we have prepared. Now, we're going to look at some basic math, so I don't want you to tune out if you're watching this. This math is actually probably more difficult to file your income tax than it would be to go along and look at the math that's occurring here. So it's just some basic algebra. And what we're looking at is really the definition of a black hole in some sense, one way of thinking about it. And the way of thinking about it here is something that we call escape velocity. So for example, we know that humans have sent probes that are on their way out of the solar system. So how can that occur? Well, if you can get an object that's traveling fast enough, the gravitational pull from the sun, if you think along that lines, is not strong enough to cause the speed of that object to decrease to the point where it stops, becomes zero momentarily, and then reverses, and then the object is heading back towards us, towards the solar system, towards the sun, let's say. So if you can go fast enough, then you can escape then the gravitational well of the solar system. In fact, we have 5 spacecraft that have done that. Can you name them, Robert, just out of coincidence?
Let's see. That would be Pioneers 1 and 2, Voyagers 1 and 2, and New Horizons.
You got the first 2, it's actually Pioneer 10 and 11.
10 and 11.
Right. And then, but the rest you have. That's right. So we have 5 spacecraft on their way out of the solar system, never to return, unless, of course, something or someone intervenes, right? So you never know what happens in the future. Obviously, we could do that ourselves, right? We could catch up to the spacecraft with our advanced spaceships and say, oh, we should put that in the Smithsonian and grab a hold of it and bring it back to Earth. But barring that kind of situation, those objects have escaped or will escape eventually, right? They'll never return to the sun. Now, the escape velocity itself, if you can imagine, how would you calculate that, first of all? Well, the kind of simple way of calculating that is what you see here listed on this slide. So the escape velocity, if you just have barely enough speed, we say that the kinetic energy then is equal to the potential energy. And here we mean the gravitational potential energy of whatever system you're looking at. So in this case, we're using the sun. And so we can just equate, which is sort of the second line you see there, the kinetic energy, which is written down simply as a half, times the mass of the particle, that could be the mass of the Voyager 1 spacecraft, times the speed squared. That would be set equal to the gravitational potential. And notice that you have the top and bottom there. The top, the numerator, we have capital G, it's just Newton's gravitational constant. We have capital M, which would represent the mass of the sun in our example. And we have a lowercase m, which would represent the mass of the spacecraft, Voyager 1, let's say. Okay. And then the potential, when you think of the object, it's divided by r, so you can think of that as the distance, right, from the Voyager spacecraft to the center. That's one way you can think about it, right? So the other way we could do is turn this around and look at, okay, what is the escape velocity then from a black hole? And so you can do the same kind of thing here. Notice that in the example that we have, kinetic energy equals the potential energy, you can simplify it a little bit. You can multiply both sides by 2. You can divide both sides by the little m, so it gets rid of that, it cancels. And so you're left with this v squared equals 2gm over r. Now we're going to look at what is the escape velocity of the object itself. So in this case, m would represent the mass of the black hole or the mass of a sun. R would be the radius of the object. Okay, so for example, the radius of the sun. When we talk about black hole, the R becomes a special definition. It's the radius of something that we call the event horizon. Now, for this example, if you think about what is the escape velocity of the sun, then the last line you see on the slide, v escape, is the square root of 2gm over r. So m is the mass of the sun, r is the radius of the sun. So that will give us what the escape velocity is. Now for the black hole, there's no hard surface. And so that's why I mentioned earlier that r would represent the distance, let's say, of a spacecraft, if you want to think of it that way, to the center of the object itself. And that's what the description is more appropriate when we think of black holes. Here we're thinking about some distance from the very center of a black hole, that center being the singularity. That would be what represented by r in this case. We want to solve for r, so you can take our expression for the escape velocity, and one way you can do it is you square both sides. So you're back to v squared equals 2gm over r. And then you set the escape velocity equals the speed of light, which is the lowercase c that you see there, and then solve for r. In this case, you get, which is the bottom line on the right side, that the radius is equal to 2gm over c squared, where r in this case is actually the distance from what's called the event horizon to the center of the black hole, which we call the singularity. So even though there's nothing inside of the event horizon, there's no solid surface that you'd run into.
Right.
We still, r would represent then the radius of that event horizon. And that just tells us then that given enough mass, the escape velocity would equal the speed of light at a certain distance away from the object. Now, of course, for the Earth, you can stand on the surface of the Earth. The escape velocity on the surface of the Earth is not equal to the speed of light. It's a lot less. But if you change that radius, that r value, and you make it smaller and smaller and smaller, eventually when that radius comes about the size of the radius of a blueberry,
Right.
then the escape velocity equals the speed of light. So you just made the Earth into a black hole, essentially. So one way of measuring the property of a black hole would be to measure what is this radius, the radius of the event horizon. Right. Anything that's inside of the radius of the event horizon, that is closer to the center of the black hole, that information, whether it's light or something else, can't get away, can't get outside to the universe itself. It would have to travel faster than the speed of light by definition.
It's stuck at that point.
Yeah, the point of no return.
Right.
It's a one-way gate. But you'd ask, well, if nothing then technically comes from a black hole, because remember the black hole's mass is all crushed to a single point in the very center, if nothing can escape that point, how can you have a temperature? And the other thing is when we have a temperature, as we'll see a little later on in some of the discussion you're going to have, is if anything has a temperature, it's also going to emit light.
Right.
So how can a black hole emit light if light itself can't escape? You have to travel faster than yourself, faster than the speed of light to get away. Now, if you want to go to the next slide, Robert, let's look at what we mean by when we talk about radiation coming from a black hole. So on this slide, notice you have this dashed circle, and that represents the circumference of the event horizon. Actually, when you describe black holes from the point of view of the general theory of relativity, which is our best description of gravity at the present time, it's actually more appropriate to talk about the circumference of the event horizon rather than the radius. The radius infers a distance, obviously, but in the coordinate system that we use to describe what happens inside the radius of a black hole, the time coordinate actually takes place of what we think of normally as the radius. So we have to be a little careful how we describe things. So that's why you might see a lot of, some books that people write about this stuff, and they always talk more about the circumference of the black hole rather than its radius. But let's go with the description that we're using here, just basic sort of fundamental classical type of viewpoint here. Now, we know that if we go into quantum mechanics, and I hate to bring that up because, yes, it can be a whole ball of wax on its own.
Yeah.
But the way to think about it, to keep it, basically simple and fundamental here, but not too simple,
Right.
is to think that all of space, there are these fields that emanate everywhere. So people have heard of the electric field. You've heard of the magnetic field. The magnetic field would be something that you would see, for example, if you took a piece of paper and put it on top of a bar magnet and then sprinkle iron filings on that piece of paper. Those little iron filings act like little compass needles, and they will change their position in such a way that they line up with the direction of the magnetic field nearest to that iron filing. And so you could see the presence of the magnetic field. It becomes visible using this trick of iron filings. And so you can imagine that there are these fields spread everywhere throughout space. Even though space may look empty in various locations, that is absent of particles, gas particles, dust particles, and so on, there are still these energy fields. Now, with an energy field, things are fluctuating when you think of quantum mechanics. It's not all the exact same value. So there can be very brief instants of time where we have a little bit more energy in a small region of space than at other times. Think of waves in an ocean where it's not flat, that there's the wind blowing and you get these up and down sort of motions. Now, out of those energy fields, particles can actually be created. They're called virtual particle pairs. So you get the formation, let's say, of an electron and its antiparticle called the positron. And over a very, very brief period of time, a really small fraction of a second, those two particles will touch each other and annihilate, turn back to pure energy, and that energy goes back into the field that was there previously. So if you can create these particle pairs, and they only last for a very brief period of time, they don't violate any known laws of physics. So you don't have to worry about that going against what we learned. Now, there's evidence for this, which we won't get into today, that these virtual pairs of particles are created and then they operate and similar to what we're describing here. But the interesting aspect of all this, and this was something that Stephen Hawking had brought up and mentioned in the 1970s, is what happens if you have these virtual particle pairs that form out of the energy of the vacuum, but it occurs right on the edge of an event horizon of a black hole? So you could have a situation where when you create these two particles, let's say they're an electron and a positron, that the positron moves in such a way that it goes inside of the event horizon, that is closer to the center of the black hole than the electron. The electron stays outside of the event horizon. So when that occurs, there is no way for that positron to meet up with the other particle to annihilate, turn back in energy, and go back into the sort of energy field of the vacuum. And so what essentially happens is that after a certain period of time, we say that the electron has become a real particle. It can escape even from the black hole. The positron has gone inside. We never see that. So we've taken virtual particles and made them real. Now, that takes energy. And what Hawking noticed was that energy then would come in the form of gravitational energy.
Right.
And that actually would have an impact on the total mass of the black hole itself. It actually bleeds energy away from the black hole, which means the black hole loses mass. Now, if you want to go to the final slide that we have here to describe that. So because we have particles coming from the vicinity of the event horizon of the black hole, it's as if that black hole is producing radiation. The thing that a lot of people have a misconception about is that radiation somehow is emitted from within the event horizon. But it can't, because that radiation is light, and light cannot escape a black hole once it's released closer to the black hole, the center of the black hole, than the event horizon itself. So the light can't get out of a black hole. But with the release, the formation, if you like, of these real particles just outside the event horizon, it looks like the black hole is emitting light. Now we can, if you like, quantify that light. We can look at the thermal energy of that light. The standard equation to describe that is the one you see here on the top line, the thermal heat energy, E, let's say, is equal to the temperature times a constant of proportionality. And that constant proportionality, that lowercase k, is known as the Boltzmann constant. That allows us to just convert temperature into energy when you multiply it by that factor of k. So then we can describe this sort of Hawking radiation as it's known today by, in terms of its energy is simply just k times t. And then that is equal to, as Hawking demonstrated, equal to another constant called little h, known as Planck's constant, times little g, which is the gravitational acceleration at the event horizon itself, if that's where we're making our calculations, which we are in this case, divided by more constants. We have a 4, we have a pi, which is just the circumference of a circle that has a diameter of 1, so 3.14159 approximately.
Approximately.
Right? And then we have c there, which is the speed of light. Now, the interesting thing in all of this is that notice that the thermal energy, or the temperature of the black hole, involves little h, which describes quantum mechanics, the subatomic physics. It's also, we have c in there as well, and that involves special relativity, right, the speed of light. The last thing that's at the top there is that little g. So what's that little g? The gravitational acceleration. That's simply Newton's gravitational constant, capital G, times the total mass of the object, so that would be the mass at the singularity, divided by the radius of the object. So in this case, it would be the radius of the event horizon, if you think of it that way. And that's squared, of course, in the bottom there. So if you put all of that together, substitute in the expression that we had in the previous slide for the radius of the event horizon, then the gravitational acceleration at the surface of the event horizon, you can think of that classically as equal to the speed of light to the 4th power divided by 4 times g times m. Now that, it seems complicated, but let's continue on to the last stage here. Now, let's take our equation that describes the temperature of the black hole, substitute in what that little g is now, which is c to the 4th divided by 4gm. And when we do that and divide both sides by k, so then we isolate the temperature on just one side, we get the final line you see here on this slide, that the temperature of the black hole is equal to h c cubed divided by 16 times pi squared times capital G times little k times the mass of the black hole. Now what do we have here? We have Planck's constant h in the numerator in the top part, so that involves quantum mechanics. We have c, and it's cubed in the top, that involves the special theory of relativity. And in the bottom, notice what else we have there, capital G, which involves gravity. And we even have the Boltzmann constant k, which involves thermal physics.
Right.
So everything is in here to describe the temperature of the black hole. Now, the consequence, and this seemed like a roundabout way, but trust me, this is the simplest way you can derive this, right? If you want it, the more precise way, of course, is getting into quantum mechanics and so on, and and getting into the general theory of relativity to describe various things, the space-time metric on the surface of the event horizon of a black hole, and blah, 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 blah. Okay, we're not going to do that.
You don't want to do that.
We're not doing that today, if ever. No, we're not doing that today. Now, the interesting thing here to look at is notice that the temperature is proportional to 1 over the mass of a black hole, which means that the greater the mass of a black hole, the lower is its temperature. Sometimes you'd think of, oh, the more massive objects would probably have a higher temperature, something like that. That's not the case here. So I put up some examples, as you can see there. If you have an object that has a mass equal to the sun's mass, 1 solar mass, if you plug that value into this equation and then calculate what the temperature is, notice you get a very, very low temperature, 2.5 times 10 to the minus 6 Kelvin. So that's essentially, 0 Kelvin for all intents and purposes.
Which means absolute zero, folks.
Yeah, so that's what, minus 464 Fahrenheit, or on minus 273 degrees Celsius.
Oh, so last Friday. Sorry.
And hopefully never to return.
Right.
We don't want that low of a temperature.
No.
But now if you decrease the mass of your object, so let's look at something that has a mass of about 1 times 10 to the 12 kilograms. Now you might think, how does that compare to 1 solar mass? Well, 1 solar mass is 1 times 10 to the 30 kilograms. So clearly 10 to the 12 kilograms is a lot less. I tried to come up with an example. What has as much mass as 10 to the 12 kilograms? And believe it or not, Robert, do you know it's estimated as the biomass of all the fish on Earth?
I find that
Fishy?
fishy. Yeah. At the same time, I know how they do and how they arrive at such a number, so it doesn't surprise me too much.
Okay, so if we use that mass value and plug this into the equation for the temperature, you get a value of about 5 times 10 to the 12K.
That's hot.
That's very hot. We don't want to be having a day as that, hot as that, right?
Yeah, that's a million, so
Yes.
that's hot.
Very hot. So that just tells you then, as the radiation is emitted from the black hole, as the black hole loses mass slowly over time, its temperature will increase as the mass decreases. And that'll just, as the mass goes down, the temperature gets hotter and hotter and hotter. And eventually what happens is that the black hole itself will what we call evaporate. And so there is a finite lifetime to the black holes themselves, every black hole. And that lifetime, of course, is very long, way longer than the age of our universe, which is roughly about 13.8 billion years. So we don't have to worry about it, in that sense. But if you're looking way far in the future, wondering what's going to happen, black holes will eventually evaporate, which is very interesting.
And they'll do so very hot, so
And
it'll be some very big explosions, I imagine.
Well, the other thing you can think of right now is the leftover heat from the Big Bang is on the order of about 2.7 Kelvin, roughly,
Right.
its temperature. That's actually hotter than the sort of nominal or average black hole that we see around, which means in that sense, black holes act like sources or sinks of energy, right? They're absorbing those photons rather than having more photons coming from the event horizon of the black hole itself. And so the temperature, the black hole mass have to be very small, or you'd have to go far into the future when the leftover heat from the Big Bang has a very low temperature for the reverse sort of situation to occur. But at some point it will. So that's quite interesting when you think of that point of view. So black holes have a temperature.
That's actually kind of impressive in and of itself. And, kind of leads to the topic that I chose, which is how are we able to take the temperature of a star like the sun or any object out in space? And to do that, we rely on spectroscopy. Spectroscopy, as I've termed it in other discussions that I've had, is the workhorse of astronomy. So how do we do that? Well, it turns out that the light emitted by a hot object, an object with a non-zero, absolute zero temperature, not only does it get brighter, as we see in this graphic, the vertical scale of the thing is the graph is the intensity, the brightness. And so as things get hotter, they get brighter. But we also see that there's motion to the left towards bluer wavelengths. So Wondergoon asks a question here, will leftovers from the black hole potentially form stars in a massive cycle, or do they eject any matter, or do we know or suspect? So I'll let that answer before I continue.
Okay, so yeah, as I mentioned about Hawking radiation, you can think of it as particles being emitted. So those particles, go from virtual to being real. So they are emitted from the vicinity of the event horizon of the black hole. Now, of course, they have a certain energy, and it would take some other type, it'd have to fall within the gravitational well of some other object before they would lose their energy to the point that they could dense enough to form, let's say, a new star. But they would just, add into the general matter of the universe itself. And don't forget, if you're dealing with a black hole of 30 times the mass of our sun, for example, then essentially, most of that matter would come out in the form of Hawking radiation or over the lifetime of the black hole after it completely evaporates. And that's not a lot of mass. That's very tiny compared to what is available, in normal galaxies and so on. And so it's negligible in that sense.
Right. So I'll give a short answer. The short answer is that while the matter is coming back out slowly but surely, it is not going to be a significant enough matter to go back into stars or anything else to produce a cycle. So, yeah. All right.
Okay.
So getting back to this, so not only are hotter things brighter, but they're also going to start being bluer. And if you think about this, if you've ever been around a fire and stuck an iron poker into the flame, it starts out glowing this dull red, and then proceeds, if you leave it in there long enough, to get orange and might start looking yellow. So the light it's giving off is brighter, but it's also getting more and more blue. Okay, that's not to say it is blue. That's just saying it gets closer and closer to the blue wavelengths. So we tend to say that it's blue. So basically, I can look at where an object is brightest, and from that wavelength of that peak intensity, I can deduce the temperature. Okay, I can deduce how hot things are. And remember, temperature is the average motion of the particles. That's going to be important in a little bit. So I can tell something about how things are moving in that object. So what does that look like? Well, in the sun, we can look at it in various wavelengths and everything. And one of the interesting facts is that the atmosphere, the corona of the sun, is actually much hotter. We're talking, it's around in the order of 1,000,000 degrees, whereas the surface of the sun, the part that's emitting the visible light that we see, is only, about 4,000 or 5,000 Kelvin?
For the surface of the sun,
Yeah,
it's 5,800 Kelvin.
5,800 Kelvin. The corona is 1,000,000 Kelvin. So why aren't we seeing the corona instead of the surface of the sun? And that will come up in just a minute. But we can see the corona. So we've got this nice satellite up there that looks in UV wavelengths called SDO, Solar Dynamics Observatory. And this is a picture of one of its wavelengths of the sun. And so we can see that there are bright spots. So those are definitely going to be hotter. Here I am gesturing with a cursor that you can't see. And we also have all these nice swirls where the material that's emitting this light, this ultraviolet light, is following the magnetic field lines of the sun. So you can kind of see that another topic is that the magnetic field of the sun is quite chaotic and different from Earth's. Another deeper ultraviolet wavelength looks like this. And so it's darker. It's not just that it's green, it is actually darker. There's less of this wavelength being emitted. But you can still see there are bright spots where it's hotter and everything else. And that's exactly what that means. And then we can do things like this, where we combine several sources. So this is combined with an X-ray observatory called NuSTAR. And X-rays are given off by basically things being so hot, particles are slamming into each other, and electrons are being stripped away. It's being ionized. And when those electrons and those atoms recombine, the photon given off is so high energy, we call it X-rays. So anything in blue in here is so hot that it's actually able to ionize the atoms. Anything in yellow and green is in ultraviolet still, so it's not quite hot enough to ionize, but we can see that we're still dealing with some very hot gas, some very hot material, and this is the sun's corona. And like I said, going back to that black body radiation, the brighter it is, the hotter it is, but also the bluer, the more ultraviolet or X-ray it is, the hotter it is. You, for instance, do not give off ultraviolet light. You are simply not hot enough. Okay? So with that in mind, the sun is hot enough in its corona, not on its photosphere, to emit X-rays. So why don't we see the corona? It should still be emitting visible light. And the answer is that it's essentially the same density as the intra-solar system medium, which is about 3 or 4 protons per cubic meter. So if you were just relying on the particles that close to the sun, you'd actually freeze to death in the corona. Because while every particle that hit you would be moving very fast, remember, temperature is a proxy for how fast things are moving. So even though the particles would be moving fast, you would get hit by a particle every once in a while because there's so few. So they're not going to transfer a whole lot of energy to you. So you'll freeze. So how do we know more? I mean, we love that we can do an indirect test like this, but we like it when we can do direct. Well, it turns out we've got the Parker Space Probe actually orbiting close to the sun. How close? Well, this is what the Parker Space Probe looks like in its folded up laboratory specimen. But how close is it actually getting? Well, there's its orbit. So it's that inner little yellow-orange orbit, and you can see clearly that it gets much, much, much closer to the sun than Mercury. In fact, I'm not sure, Wayne, maybe you know, does it actually enter the corona?
Yes, really.
It does.
Yeah, because that extends out to millions and millions and millions of miles, and it varies, of course, it fluctuates.
Right. So
Definitely.
it actually gets into the corona. So we're actually got a device out there right now that's taking direct measurements of how fast things are moving in the corona. Now, its real purpose is, of course, to look at the magnetic fields and the solar seismology, and, you know, because the big question for us is, how does the corona heat up? I mean, you've gone from 5,000 Kelvin at the surface of the sun out to 1,000,000 Kelvin in the corona. How do you heat back up as you move further away from the center? And that's the question. And I would recommend, if you're interested, join us in the physics department here at UND, learn the physics, learn some astronomy, and go win your Nobel Prize.
If it was that easy.
Yeah, if only it were that easy, right?
We'd all have fun.
But, you know, that's kind of the question is how does it heat back up like that? When, you know, I mean, we're getting close to core temperatures in the corona. So things are sped up and accelerated quite a bit. And how does that happen? What's going on? The answer is we don't know, but we're going to figure it out.
Okay, so Robert, talking about, you know, we don't know type of thing. You know, something else we don't know?
What's that?
Is there life elsewhere in the universe besides
now
the
that question.
Oh, how's that to go? Do you want to describe what the Fermi paradox is?
That one I can do well because I get asked that question quite a bit. The Fermi paradox was first proposed by the gentleman who it's named after, and that's Fermi.
Enrico Fermi.
Enrico Fermi. And he first posited that, you know, with the universe as big as it is and everything, where are the aliens? Where are the other civilizations? Why haven't we heard from them? Why haven't we had contact with them, for that matter? And he did not propose really any answers. He simply asked the question first, where are they? And we have since concocted all kinds of answers for that. I have my own favorite answer to it, but I think in bringing up the question, you have some other thoughts that you want to bring up.
So maybe we should do the disclaimer.
Yeah, these are just the opinions of myself and Dr. Wayne Barkhouse. These are not the opinions of the University of North Dakota. You get the idea.
By the way, did you notice there's somebody like right behind me looking at me?
Oh, yeah, Mr. Einstein.
Did you notice that?
I did.
Okay. You know why he's there?
Mm.
He's there to keep us on the straight and narrow.
Okay.
Make sure we don't goof up. You see, he will give us a little kick in the backside to tell us what's right and what's wrong. So,
Clunk you in the head with that yo-yo.
now, Robert, there's been a lot of work done. I guess you would say the first time in the 1960s when Frank Drake did the first kind of search looking for signals with a radio telescope. Now, at the time when that experiment was done, nobody quite knew if the waves, you know, the electromagnetic waves are full of broadcasts coming from other civilizations and a really noisy, you know, place to be. For example, you hear lots of stations if you tune on your AM radio, or if it's just deadly silent.
Right.
That there's no life anywhere else, at least none that are broadcasting or that we can detect with the equipment that we have at this time.
Right. Well, I would point out on that point, you know, people talk about how, yeah, aliens, the first impression they're going to get of us is Hitler at the World Olympics. Well, that's not necessarily true because we don't have anything big enough to detect that signal at the distance it would be from the Earth. It's very faint at this point. That energy is over a huge area. So maybe it's not that big a deal, and maybe that's one answer.
Well, a lot of the AM broadcasts get trapped by ionosphere too.
Right.
You know, just a little bit of it leaks out, so you've already diluting away that signal before it even escapes the Earth environment in that sense, right? So
Right.
it'd be very difficult. But you know, with the technology, with the large enough radio telescope, we do have military radar that's extremely powerful.
Right.
And those signals do leak out into space. So under the right conditions, some advanced civilization certainly can tell that we're here.
Right.
Which gets into the idea of, you know, should we purposely broadcast things out into space? And this has been done in the past. You know, a well-known one was, there was a broadcast done by Arecibo many years ago, and it was broadcast, if I'm not mistaken, to a globular cluster M13, which is the one that you see in the constellation Hercules.
Right.
It's kind of a favorite target with a small telescope in a dark site. But should we be doing that? In other words, should we be letting other life forms know on purpose that we are here? You know, accidentally, I mean, of course, we can't stop that. At least what has happened in the past has happened.
Right.
We could stop, of course, in the future, signals leaking out. We could go to fiber optic cables and we become quiet on the radio dial, if you like. But should we purposely, you know, send out a signal to let other life forms, if they exist, that we're here? And a lot of people think, you know, that's like yelling in a jungle. If you're in the jungle somewhere at night and you start screeching to let animals know that you're around, that may not be a good idea.
Right.
So that's the kind of the argument some people make. In fact, others have argued that I heard that we shouldn't do that independently. It shouldn't be our university or any other university. In fact, it shouldn't be another country that does this, that we should go to the United Nations and that the world should agree whether or not we should do such a thing. Because obviously it impacts the world, not just one country, right?
Right.
So what are your thoughts on that, Robert?
I'm going to come out as wishy-washy because I'm of many different minds on that. I think there's merit to that because, you know, as I put it, it doesn't take much intelligence to sneak up on grass. So I'm a firm believer that any intelligent species is going to be an omnivore or carnivore. And as such, what happens when you put, you know, more than one omnivore or carnivore in the same environmental niche? The answer is generally speaking, one's going bye-bye, one's going away. And if they cross interstellar space, I know who my money's on, and it ain't us. So there's definitely some validity to the opinion that we ought to go radio quiet. But at the same time, how can we with the modern world being what it is? And we're not there yet. So it's really not a choice anyway.
Now, some people would argue, and they have argued in the past, that we shouldn't do this sort of searching.
Right.
Because it's a waste of money. Now, there was a program that was done a few years back, I think it was in the 1990s, that NASA had started, so obviously that's American taxpayer money that was going to be used for their SETI program, and then that went went along a little ways. I don't think they got too far into it, a year or so, when it was killed by Congress eventually.
Right.
So the money went away. So now most of it has been private money.
Right. And at that point, I'm sorry, the public doesn't get much voice in it.
Well, you could always argue that that money's better spent, doing other things rather than spending it on buying radio telescope time at different facilities around the world. But,
I'd kind of like to know if we are alone, personally.
Right, so that's a very important question. And so from the point of view of statistics now, you can often wonder, okay, what do we need for life? Well, we're biased right away.
Right.
Because we know of life only existing in one location, that is on the planet Earth. So you can think of what do we need then for life to arise as it does here? Well, we need a planet, obviously. We don't expect to arise on the surface of a star, for example.
Right.
We need some kind of energy source, so let's say we need a nearby star. That star can't be too close or it's going to be really hot and the environment was not conducive for the formation of life as we know it.
Right.
That star can't be too far away from us or it's just too cold or an absolute
There's not enough free energy.
Yeah, that's right. And life wouldn't arise on that type of planet. And so people often wonder, why did life arise on the planet Earth? Well, it just so happens that we're in that right Goldilocks position where things are just right. Doesn't mean that life is going to form, of course, but it did form or we wouldn't be here talking about it, obviously.
Right.
So we have the one example. So let's say we need a planet. So it wasn't that long ago, and prior to the mid-1990s where we didn't know that we didn't have any evidence at all for planets being around any other star.
Right.
And so people wonder, oh, that is weird because, we've been studying astronomy for hundreds and hundreds of years. We certainly had half-decent telescopes all the way into the 1990s and beyond. Why did it take so long? Why aren't we finding these planets? And eventually, planets were found. Right? We can see if you like, the influence of the gravitational pull of the planets on the host stars. So we see stars wobbling around. We can see planets transiting or moving in front of the star, which slightly dims their light and so on. So once we realize the techniques and how to manage it, if you like, how to utilize those techniques better, then we started discovering planets. And of course, with the advancement of technology, you build spacecraft, put them in space like Kepler and TESS, whose specific purpose is to find these planets, which we call exoplanets, is a term that we generally use today. Then we literally have seen evidence for thousands and thousands and thousands of planets.
I think they recently celebrated the fact that they got over 5,000 exoplanets now verified. We know they exist.
Right, so the point of view of statistics, that you could say statistically every star has at least one planet in orbit around it. In fact, after a while, we might be able to say that every star statistic has several planets orbiting around it.
Right.
So then we can estimate what is the number of planets then that's in our own galaxy, the Milky Way. Well, there are 200 billion to 400 billion stars, we estimate, in the Milky Way galaxy. We can't see every individual star. So it's not like we can count them all, even if we had the time and we had an army of graduate students that are willing to sit down and count the individual. Of course, nowadays you do by computer software, right?
Yeah,
So
maybe we ought to do a show, part of a show on statistical counting methods.
there we go. But you can estimate, therefore, that there should be literally 200 billion to 400 billion planets in our own Milky Way galaxy. And people have estimated that there are at least, a trillion other galaxies in the observable universe. So take 1 trillion, multiply it by, let's say, 400 billion. That's the number of planets in our universe. And you always ask that question, of course, what's the chance of life only forming on one of those planets? It seems to be very tiny. The fact is, statistically, there must be life somewhere else.
Somewhere.
The problem, of course, is finding that life.
Right.
And what we can do, of course, is get access to things that are nearby, like other planets in our solar system. Right now, there is no evidence for life living right now on other planets unless it's in the form of microbial type life. You could have that buried underneath the soil on Mars, for example. It would go under the soil to stay away from the ultraviolet light, and therefore it might be hospitable enough for that form of life to exist. We've had cross-contamination of life from Earth to other planets, and we know that that must be the case because we recognize that there are meteorites that are here on Earth that came from other planets like Mars.
Right.
So if rocks can go from here to Mars, let's say in the past we had an impact and it was enough to jettison a rock into space and eventually it impact the surface of Mars, as an example, if there were any type of microbial life on that rock in the interior, so it survived that journey, then there would be life then on Mars.
And in the interior is the important part.
Yes,
Yeah.
exactly. In fact, we've sent probes, landers on the moon before men first landed on the moon in 1969. They're Surveyor spacecraft, Surveyor landers. And when they brought part of the Surveyor lander back from the Apollo 12 mission and analyzed it, they found bacteria growing on the surface of that lander. And so as far as we can tell, it was on there when it was launched from the Earth, and it survived for many months on the surface of the moon in the vacuum of space. So some of these life forms are pretty hardy. They can survive harsh conditions compared to us.
Right.
Okay. So when you get outside of the solar system, then is there life elsewhere? And so you get into this whole genre of UFOs and aliens and all that kind of stuff. And so people have been putting their money into trying to look for signals coming from other civilizations, what today we call techno-signatures, for example. And one of the well-known things that's going on now is the Breakthrough Listen project. And so people are spending money then to try to survey different stars, large sample of million stars or so, using our radio telescopes, listing, for each star for a period of time, then moving on if they don't hear anything unusual to another star, and so on and so forth. And so you might have noticed there was a recent story that came out where this team looked at, from the point of view of advanced computer algorithms, looking at signals that were recorded coming from a sample of stars. And according to them, there were 8 signatures that they detected in their computer algorithm, which was supposedly more sensitive than the algorithm that had been run on the data initially. You do your first pass through the data, but you record that information, it's not lost, you don't delete it, and then you can analyze it later when you have time, if you like. And
or because you've got better techniques or better equipment.
Exactly. And they found something from 8 of these signatures, which represent a total of 5 stars, that looked very interesting, that essentially require follow-up work.
Cool.
Yeah.
And, and to kind of tone things down, though, I'm skeptical enough that I want confirming observations. Having one signal that looks interesting is nice, but you really start going, when you get 2, 3, 4, and all of a sudden it's like, okay, not only is this signal interesting and possibly technological in its basis, but now we've got 2, 3, 4, 5, 6 repeat detections of this signal. At that point, I'm willing to concede, hey, we found ET.
Well, think of this scenario. These signatures turn out to be bogus.
Right.
In fact, everything we discovered turns out to be, interference from Earth, for example, that happened to leak in the side lobes, as we would say, for a radio telescope. We get detected by the radio telescope, but they're not stuff from other stars. They are actually from earthly things.
Right.
And we watch, and we listen, and we look, and we do this for year after year after year after year. And this goes on for 100 years.
Right.
Now, we've been listening since 1960, on and off. Okay? So it's been a few years now. And this continues for another 100 years. And we don't hear anything. What type of conclusions would we come to at that point?
I would conclude that there's definitely no one nearby.
No one nearby.
And that's astronomically nearby.
Right.
So, I'll put a figure on that. I'll say within 1,000, 1,500, somewhere in there, light years.
Now, what's a pessimistic view? It could be that life arises, advanced life occurs. Life, and what do you mean by advanced or intelligent life? Well, let's say life forms that can build radio transmitters, radio receivers.
Absolutely.
Okay? They go through their industrial revolution. They go through their computer revolution. That's something we're going through, the information age today, as we hear about a lot. And eventually they just can't get along with each other.
And they wipe each other out.
And they wipe each other out. Which means that there is a period of time in which the civilization existed, in which they are broadcasting, either purposely or not purposely, and which would allow us to detect them. But here's the thing to think about. The Earth's been around for about 4.5 billion years.
Right.
That's a B, billion.
Right.
Okay. The universe has been around for 13.8 billion years. So the universe has been around for about 9 billion years or so, roughly, before the Earth even came along.
Right.
And along with that, the sun. So the sun would have formed at the time that our solar system formed and so on. So there was no sun, there was no Earth for nearly roughly 9 billion years. But other stars were certainly around. Our Milky Way was around.
Right.
So imagine that life got a foothold on a planet orbiting another star, and that star formed along with that planet, let's say 5 billion years before our sun and the Earth formed.
Right.
So they have a 5 billion year head start. Okay?
Yeah, and that gets into my favorite answer to the Fermi paradox, but I'll go ahead and let you finish.
Right. So there is a possibility that life has arose in multiple places around even just our galaxy, if you're not worrying about other galaxies, and that those civilizations had a finite lifetime because they ended up destroying each other eventually.
Right.
And that would explain why we've been looking since the 1960s and haven't heard anything, is because the probability of some civilization that's broadcasting now that we could hear, for the number of stars in our galaxy, that probability may be zero.
Zero. And John Novak asks a question of, what about the possibility that extraterrestrial life doesn't deem us significant enough to contact?
That's a possibility, but even bacteria existing on Mars, that catches our attention.
Right.
So if this civilization hasn't encountered any other life forms, they would be certainly interested in us. Because we're not just bacteria, obviously, right? We have our own technosignature that leaks out into space. So from that point of view, I would assume they would be interested.
Right.
If they've already encountered over their history thousands and thousands of other planets that had life forms, then maybe we're not that so different after all. Right.
Right.
So that would all depend.
And they may be waiting to see if we do pass through the era of wiping ourselves out. And
Maybe.
that's a possibility. But my answer to the Fermi paradox gets into what you're talking about, that the universe existed for 9 billion years before the sun. But during that time, what was most of the universe? Hydrogen and helium. Show me life made out of hydrogen helium first, and now I'll believe that 9 billion years of time has passed that could have produced intelligent life, much less intelligent life. What I'm getting at is all of the carbon, iron, everything else had to be produced, mixed in, and then incorporated into stars. So my answer is that we're one of the elder races. We're one of the first to emerge. Now that still is plus or minus a few 100 million years.
Well, I would go against that.
Oh, you would?
If you don't
Okay.
mind.
No, I don't mind at all.
Because if you're looking at whether or not there's enough carbon and iron and those kind of heavy elements that get produced inside of stars, one of the things that we can do, of course, is we can look at galaxies that are very far away. And because of the finite speed of light, right, we're seeing them a long time ago. And a lot of those galaxies do have those heavy elements.
Okay, good point. Excellent point. So, yeah, we were talking about something along that lines earlier about the fact that some of these older galaxies that we're seeing very far away have high metallicities and are therefore redder than they would be expected.
But that's a good topic, I think, for the next podcast.
I think so too.
Yeah. So I want to thank everybody for listening today, and sorry about the problem we had at the beginning. We'll work on the technical aspect of
We'll
things.
work on that.
Our next podcast, of course, is next Tuesday. That's on February the 14th, Valentine's Day.
Yay!
So we'll really put our heart into getting everything to work. How's that?
Put our heart in it. Yeah.
But today I want to leave you with a quote, and this one's actually from Isaac Newton. So his quote is from a letter that he wrote to Robert Hooke, and which became a bitter enemy of him later on in life. But at this point, he was still a friend of Newton's, and it's dated from February the 5th, 1675. And the quote from Newton is, "If I have seen further, it is by standing on the shoulders of giants." And so I want to thank you for listening. Thank you for contributing to the live chat, Robert.
Thank you.
Okay, thank you.
Thank y'all for joining in our chat, and thank you for helping us work out partially our technical difficulties.
And we'll see you next time.
We'll see you
Thanks.
next time. Bye.